Welcome to the 10th lecture video for Physics 4B. We continue our efforts from last week, further developing the electric field concept, as we prepare to introduce Gauss's law, one of the fundamental laws of electricity and magnetism, in the next lecture. In the first couple lectures here, we work out electric fields of two additional geometries of charge distributions using direct integration. We do this for two reasons. One, this will give us formulas that we can use and compare to later. Two, the demonstrated difficulty of this approach will draw a stark contrast to how easy application of Gauss's law is when correct symmetries are utilized. The remainder of this lecture set is used to build intuition and familiarity with the tools and mental images that will be helpful as we introduce and apply Gauss's law in the next lecture. Familiarity with the electric field lines will be particularly important. We will properly introduce Gauss's law in the next lecture. In addition to being a key fundamental law of nature, in the right situations, it can also give us electric field formulas in a few quick steps, unlike direct integration. Hi, this is the second of the three lecture snippets for the calculation of electric field through integration. Now, these three examples are specifically chosen because electric field for these exact three situations can be calculated using Gauss's law. And by comparison, this will illustrate the power of Gauss's law and how much it makes your life simpler. Now, there are other cases where you actually cannot use Gauss's law, and you do have to use these techniques. So for that also, it's good for you to know how to do this if you have to do it. So this is a calculation of electric field due to an infinite plane. So I'm going to set up a plane in the vertical direction and imagine a point here, and you are trying to calculate an electric field at this point due to this plane, counting up all contributions from all the different parts of the plane. So let's start. Let me draw a representation of the infinite plane of charge in a perspective view. All right. I'm drawing the boundaries for the plane, but you should imagine the plane being infinite without boundary. So we are interested in the electric field at this point here at some distance d from the plane. So let me set up my axis for setting up this calculation here. I'm going to say that the plane is on the xy axis. So here it would look like x-axis coming towards me, y-axis upward, and the z-axis to the right. So this will be my x, y, z-axis. So we are going to use Coulomb's law again also. But as with the last time, we have to break up this plane into tiny little pieces so that for each one of those pieces, we can say it looks like a point charge. So let me pick a representative point here. I'm going to pick a representative area element. Let me draw some guidelines here. So these are guidelines for where y is equal to 0. And these are guidelines along where x is equal to 0. So let me pick a point here. This will be at some coordinate y and at some coordinate x. And it'll be at some distance from this point. Now, because I'm trying to draw a three-dimensional thing in two-dimensional surface, I want you to use your imagination what this distance should look like. When you go through the geometry exercise, trying to figure out this distance here, you should get square root of x squared plus y squared plus d squared, square rooted. So that's going to be distance from this little element of charge to the point where we are trying to calculate what is the electric field. So we use Coulomb's law again. As a reminder, this is the Coulomb's law. Coulomb's law says that electric field due to a point charge is equal to K charge of the point charge divided by distance squared. And because it's a vector, I have to multiply by r hat. So here, r hat vector would be an extension of this line that we have drawn from the charge to the point. So let me extend it by a little bit and label this as my r hat. All right. So once again, we start by saying this small part of the overall charge contributes a small amount of electric field, dE. And this small amount of electric field, the magnitude is given by Coulomb's law, K times the amount of charge. Oh, I forgot to specify the charge density of this plane charge. Let's say the charge density is sigma. And the way charge density is defined is the total amount of charge divided by the area. So if this was an actually infinite plane, then it would have an infinite amount of charge. So here, to get the amount of charge that's in this small area element, it'll be sigma times the area of this element. So that should be this. Sigma times the area element will be the width, dx, times the height, dy. That'll to give me the area of that little piece that you're seeing. So that's the numerator. The denominator is distance squared. We have distance worked out like last time. So when I square it, I get x squared plus y squared plus d squared. Oh, and because it's a vector, I have to have this r hat vector. All right. Now, figuring out this r hat vector takes a little bit of work. So I'm just going to do this quickly, and when you do multivariable calculus, you will learn all this. Let me draw a representation of that r hat vector in this axis that I have drawn here. So the r hat vector should look like something like this. This is close enough to the r hat vector. Then there are two angles that I can use to characterize this r hat vector. There's the angle with respect to the z-axis. I'm going to label this with the symbol theta. In your multivariable calculus class, they will actually use phi, but I'm going to use theta is the physics convention. And for the second angle, because this is in three-dimensional space, you have to imagine a projection of this vector onto the xy plane. So I guess I had this vector go in the both the negative and negative y direction. So when I take the projection, let's say a projection along the xy plane looks something like this. This is the projection. Then the angle with respect to the x-axis, that'll be phi. So when you write out the r hat vector with these parameters in mind, then the r hat vector is equal to cosine of phi times sine of theta x hat plus sine of phi times sine of theta y hat plus cosine theta z hat. All right, it's already getting pretty complicated. By the way, in your textbook, they do this in a way where they use the information from the previous problem with the infinite line. That would be probably an easier way to do it. I just want you to show the most difficult way possible. So to figure out each of these, you draw the triangle again. But here is a shortcut of a sort. So let me give you the answers to this without proving them. If you want, you can go through the triangle drawing exercise and prove this for yourself, but the idea here is that you would never actually have to do this. So let me give you the x component first. So the x component is x over square root of x squared plus y squared plus d squared. It's a surprisingly simple expression. And the same thing for y component. It's y over square root of x squared plus y squared plus d squared. And what do you think the g component will be? Well, if you guessed d, because that's the g component of this long vector, d over square root of x squared plus y squared plus d squared. If you guessed that, you would be right. So those are the three components of this Rth vector. So let me write that all out. Okay, so all of this is equal to, I'm not going to write k sigma dx dy every single time, so let me just write it out once. K sigma dx times dy. And I'm going to factor out this common denominator for each of these three terms, so that this common denominator outside here will be x squared plus y squared plus d squared raised to the power of 3/2. All right, so the remaining parts of the R-hat vector is x times x hat plus y times y hat plus d times z hat. All right, so to calculate the total electric field, we are going to do the same thing as before. We are going to integrate this expression dE over the whole plane. So what that whole plane means is now we have to do the double integral, because the plane is a two-dimensional object, and you can actually see it here. We have two integration variables, dx and dy, multiplying to each other. So we are going to have to do double integrals, one with respect to x and another with respect to y. So it will be x and y from negative infinity to positive infinity for both of them. And when we complete all of this, we are supposed to get the total electric field. Now, when you look at this carefully, you will realize that we get similar simplification as before. The simplification we had last time was that last time the y term went away because the term with y was an odd function. So when you did integral over a symmetric interval, it added up to 0. Here you see the same thing. So with y component, it's a function of y. That's odd. Here the denominator is even. So this times all of this is an odd function of y. So when I do the integral with respect to y, it's all going to go to 0. So let me do that and save myself some effort and space. This is 0. And the same thing happens to the x, because this time we are integrating with respect to x also. So let me cross this out, and x goes to 0 as well. So this time also, there's really only one component that doesn't go to 0. So let me write it out. Let's move those expressions first. Okay, so we are going to write the simplified version. So we have integral with respect to x going from negative infinity to positive infinity. Let me pull out dx up to this far, because the dx doesn't depend on y. I can pull out this far. And that comes after having done the integral with respect to y, going from evaluated from negative infinity to positive infinity dy. So the whole integrand, having factored those two things out, is k sigma d g hat over x squared plus y squared plus d squared raised to the power of 3/2. All right. If this is beginning to look similar to what we did the last time, then yeah, it is similar to what we did the last time. So this is not an easy integral. We have to use Wolfram alpha. In fact, after you guys remember what the form of the integral looked like after the first integral. It wasn't any simpler then. So the second integral is going to be even more complicated. So let me semi-admit defeat here, because this is the difficult integral that if I try to do it by hand, this video will be an hour long. So I'm going to push as much as possible to Wolfram alpha. Let's see if Wolfram alpha will do double integral. So I don't need to enter k, sigma, or d because they are constant, or g hat. So I'm going to be integrating 1 over x squared plus y squared plus d squared raised to the power of 3/2. And this time I'm going to do definite integral. That's me pushing off as much work as possible to Wolfram alpha. And let me try to specify this in natural language and see if Wolfram alpha understands it correctly. So I'm integrating this from x equals negative infinity to x equals positive infinity, and also from y equals negative infinity to y equals positive infinity. I'm hoping Wolfram alpha will understand that means double integral. We'll see. All right, that is the input I meant. And oh wow, there is an actual answer to that. Where is that pi coming from? So whenever I see pi, I assume there was some trick substitution reason involved that I don't want to know about. All right, let me copy this off to my board so that I can continue from there. Okay, now I can refer to that to write down what my integral should be. So I can say this whole thing is equal to, there's still g hat. So the electric field is in the direction of g hat. Hopefully that matches with your intuition. Times k sigma d times, and now the rest is where the integral comes in. It's times 2 pi over square root of d squared. I think this is because Mathematica is assuming that d could be a complex number. I know d is a real number, positive in fact, so let me simplify that just to d as I'm writing it down. All right, that's it. That's the answer. Oh, look at how it simplifies. Looks like d actually cancels out. So I get an expression for electric field that does not depend on distance. So let me write down the full expression. The full expression is electric field as a vector is equal to, I have k sigma and 2 pi. So 2 pi k sigma times g hat. That's it. It's a constant value. It's a very simple answer that that is surprising given how difficult this would have been mathematically if I didn't admit defeat and use the Wolfram alpha. And this is what you will see when you see the application of Gauss's law. Using Gauss's law, this problem can be done in less than 5 minutes. I've done it in class in less than 5 minutes. And while doing it in less than 5 minutes, you don't have to know all this multivariable calculus stuff that I didn't bother explaining because I knew explanation would take so long. So this is the calculation of electric field using integration for the infinite plane of charges. And As you can see, the result is pretty simple. But if we were trying to approach this with integration method, the calculation would have been very complicated. All right, I have one more example. I traditionally don't do this example in lecture because it's way too complicated. But hey, I'm making a video. I can edit it. So I thought I'd give it a try. So I'll see you in the next video. Hi, this is the third of the 3 lecture snippets on using integration method to calculate electric field due to an extended body. So this is the third example that I usually don't do in class because usually by this point we've wasted enough time trying to do this and it was time for me to illustrate Gauss's law method. But this is a video, you can watch it, you don't have to watch it, so I thought it would be fun to do it. Now, this is mathematically the most complicated, but I think this is a good opportunity for me to explain some of the multivariable calculus stuff that I skipped over in the last example. So the example I want to work out here is electric field due to uniformly charged sphere. So let me start out with the illustration of the sphere. Let me draw the picture large enough so that I can label different parts of the vector and so on. Let me start out with the axis first actually. So the axis will look like x-axis here, y-axis, and z-axis. So the sphere would look something like this, of radius r. And let me just draw a little circle here as a reminder that it's a solid sphere, not just a circle. Let's say that the radius of the sphere is capital R. I'm going to need 2 different variables to indicate 2 different vectors. Traditionally, people use lowercase r and lowercase r prime, but I think the prime is going to get lost easily. So let me use a slightly non-standard label. So the question here is this. So given a point here, for example, what is the electric field at this point? Let me indicate the position of this point with a vector r. Now, I am going to need to count a contribution from all the different parts of this uniformly charged sphere. So let me take a little chunk here, for example. So I'm trying to take a chunk in a way it conforms with the spherical symmetry of the setup. I will describe in a bit how this chunk is exactly taken, but it comes down to I need some letter symbol to describe what is the position of this chunk. And that's going to be a vector also. And this is the one that's traditionally labeled as r prime. Once again, I'm afraid the prime will get lost here and there. So let me use the letter S to indicate this position here. Once again, this is going to be slightly non-standard. When you take upper division electrodynamics, letter S is actually used for the radius in cylindrical coordinate system, but so go with it for this one, please. So that's the setup. I have all these different points contributing to the electric field at this point here. So I need to use Coulomb's law with these infinitesimal portions of uniformly charged sphere. Let me write it down on the side as a reminder. Small contribution to the electric field is equal to K times the small amount of charge in that part that's contributing divided by distance squared. So here the distance is best represented by a vector going from the tip of S to the tip of R. This is the distance vector. Now, as you look at this, if you're thinking, oh, expression for that unit vector that I used to draw, the unit vector, pointing this way, r hat, If you're thinking that's going to be complicated, well, you'll be right. So what I'm going to do is I'm going to rewrite this expression so that I can more easily mathematically express this in full form. So before, this is what we used to do. We would say, all right, so this is actually a vector, and there's going to be this r hat that I'll define later. Well, let me take it back. So it is going to be a vector. But the thing about this r hat here, what's special is that it's the vector going along the direction of d. So let's replace that with not r hat, but d. That'll give me the correct direction for the direction of this small contribution to the electric field. Now then, this d vector is not unit vector. It doesn't have a length of 1. So I need to fix that. The way I would fix it is by dividing it by the absolute value of d. Mathematically, the best way to represent it is this way. Instead of d squared here, I'm going to write it this way. The vector d, dot product with itself. So that's the length of d squared. I'm going to need square root of this and then 3 of those factors. 2 of them for Coulomb's law and 1 of them to cancel out this length of the d vector, giving me effectively the unit vector. So I'm going to say this is going to be raised to power of 3/2. Alright, so this is the form of Coulomb's law that I'm going to use for this problem. It'll help me set up an integral. The integral will look hopelessly complicated, and I'll resort to Mathematica again. So I should do some intermediate work. Let me start out by writing down what these s, r, and d vectors are in terms of x hat, y hat, and z hat. Let's start there. R is the easiest to write down, so let's do that. So the vector r is going to be, it only has the z component, no x or y component. So I could write that this is equal to its own magnitude, r without the vector, times z hat. That's the vector r. Alright, vector s. Now that one's a little bit more interesting. So I'm going to use spherical coordinate system. So in the spherical coordinate system, this is the way we label it in the physics class. We label the coordinates, the angle of the vector that it makes with the z-axis, we label it theta. That's the angle that your multivariable calculus class would label phi. We just swap those letters. It's just different conventions. And for the other angle, I have to consider the projection of the vector s onto the xy plane. So let's say this is the projection. I know in the this figure, it's kind of hard to see. So once you take the projection, which would have length s sine theta, then I find this angle here. And this angle is what I would label phi. Once again, your math class and physics class will just have two different conventions. So with these two angles and the distance from the origin, we can specify this vector. And when you do, this is the expression that you get for this vector s. It's the same expression that you saw last time, except with the length s. So it's going to be, for the x component, s cosine phi times sine of theta x hat plus, for the y component, s sine of phi times sine theta y hat plus, for the z component, s cosine theta z hat. Alright, we're almost there. We need an expression for d. And this figure gives the best way to get at d. D is the vector connecting tip of s hat to r hat, which means we could actually say this. We can say that the vector d is actually given by difference between these two vectors. So adding it back, it should be r minus s. I know this is correct because if I add this, back to S, then I should get R. That's what you see. S plus D gives you R. All right, so that's D. I can write it out in the component form. So it's the S that has all the components, and R has only one. So it's going to be minus S cosine phi times sine of theta x hat minus S sine of phi sine of theta y hat plus R minus S cosine theta t hat. All right, that's the D vector. I think we have everything we need to write out this infinitesimal contribution to the electric field. I should probably specify the charge density of this sphere. Let's say that the charge density of sphere is given by density rho. Remember the symbol Greek letter rho that we use for density, mass density? We also use it for charge density. So looking at the contribution from this small element here, what we are saying is that the small contribution to electric field, dE, as a vector, is equal to K times the small amount of charge. That's going to be the density times what's going to be called volume element. I will work out this volume element on a separate page because that itself is a little bit of multivariable calculus that you have to know for this question. So I will do it on a separate page after I finish writing this down. This divided by, I have the denominator here. So what I'm going to do is I'm going to take the D vector here, take a dot product with itself, which means x component squared plus y component squared plus this component squared, and then raise to the power of 3/2. So this is x component, s squared cosine squared phi sine squared theta plus the y component, s squared sine squared phi times sine squared theta plus the g component squared. So that's r minus s cosine theta squared. All right, all of this raised to power of 3/2. All right, it looks like I'm kind of running low on space. All right, let me just write D as a vector here. If you stare at this for a while, you'll realize you can actually simplify some of this a little bit. So let's do that. I see cosine squared phi, and the rest are the same as here, except for the sine squared phi, which means you can imagine writing this down. So this would simplify into s squared vector out sine squared theta times cosine squared phi plus sine squared phi. And this is just 1. So I can combine the x and y components here and get a simpler term. And I guess I can leave it up at that point for now, and I'll come back to the rest. So simplifying what I have here, k rho dv over s squared sine squared theta. This is the result of combining x and y components, plus the g component is still there, r minus s cosine theta raised to power of 2, the whole thing raised to power of 3/2. All right, now I think I have room for D, so let's write it down. D is given by minus s cosine phi sine theta x hat minus s sine phi sine theta y hat plus r minus s cosine theta t hat. All right, that's the vector D. Okay, I believe this is the time to address this dV. So let me bring up a new page and we'll talk about it. All right, on this new page, I have my sphere drawn even bigger so that I can draw more clear figures to talk about it. Let's say we are talking about a volume element that's just about on the surface of this sphere. That doesn't make it any less general, since I can sort of imagine imaginary spheres that's smaller than capital R and do it for, yeah. Okay, so if you'd like, you could consider this to be the sphere of radius S for the particular radius S that you're considering. So this is what's called volume element, dV. And I'd like to label each of the sides and see if each of those sides makes sense. All right. So one side is pretty easy to label. It's if you have this S vector pointing out here, then you can label this side here. That's the thickness of the sphere or spherical shell, or I could call this ds. That's how much S would vary within the volume. All right. I need to get two more sides. This side here and this side here. Now, the first side I drew is actually easier because you know that this is part of an arc of a circle that goes from pole to pole. So if you imagine drawing a gray circle that goes from pole to pole, then this length would be the radius of the circle, S, times the angular displacement. So this is what I can call S d theta. So that's the length of that side. Now, length of this side is a little bit trickier. You have to imagine taking a projection of all of this onto the xy plane. So let's say this is the xy plane. And that length that I have drawn up there, it's represented by this. So here the radius is actually not S. Here the radius is S sine theta. So this projection here would be S sine theta times the small change in the angle phi, d phi. So with all of that, this side here is S sine theta d phi. So this is a quick overview of the spherical coordinate system. You are not expected to know this for this class. You will be learning it in your multivariable calculus. So the volume element is essentially product of these three sides. The idea is that when you're talking about infinitesimal volume, as long as these are all relatively perpendicular to each other, then we don't care that they are all curved. If you take the small enough sides, then the fact that it's curved shouldn't matter. So I can say the volume element dV is equal to product of ds times s d theta times s sine theta d phi. Or if you want to make this all look pretty, you could say this is equal to, factor out the two factors of s in front, s squared, and I have one function of theta, sine theta, and all the infinitesimals together, ds, d theta, d phi. So that's it. That's the volume element. Let me go back to the other page and plug this in. All right, so I'm ready to plug in the volume element. So let me erase this dV and plug in the volume element. All right, that's it. So to get the total electric field, so this is the infinitesimal electric field. And if I want the total contribution, then I would integrate this over the volume of sphere. So this is going to be a triple integral. So it's integral with respect to ds, d theta, and d phi. And when I finish that, then I'm going to get the total electric field E. So I'm going to go over the integral with respect to other two variables in a bit. But let me first consider the integral with respect to phi. So phi is the angle along the xy plane. It goes from 0 all the way around to 2 pi. So phi will go from 0 to 2 pi. And if you stare at this expression long enough, then you realize something. A lot of the expressions here, they don't depend on phi. In fact, there are only two terms that actually depends on phi. Here, the x component here, and here, the y component here. And in particular, they depend on as cosine of phi. What do you think you'll get when you integrate cosine of phi over a whole period, 0 to 2 pi? If you said 0, you're right. Yeah. So this term is going to vanish. The x component is going to go to 0. And the same thing happens with the sine of phi. When you integrate it from 0 to 2 pi, it's going to give you 0. And there's no other phi terms there, so phi integral is really that simple. And it really that simply evaluates to 0 for x and y component. Hopefully that makes intuitive sense. When you look at this setup here, well, we said that this is the sphere and the point is here. Hopefully your intuition tells you that the electric field only points in the z direction. That's what this mathematical cancellation is showing. So that's good, actually. We were able to get some meaningful result out of it. So let me actually write down this simplified expression here. So the electric field, let me just say g component of electric field, since that's the only component that will be remaining. That's going to be equal to integral. Let's be careful here. I want to do the s integral last. So let me call this ds. S is going to go from 0, very center of sphere, to the whole radius of the sphere r. And then I'm going to do the d theta integral next. I mean, before s integral. So theta is actually going to go from 0 to, this is where you have to be careful. When you look at this sphere here, so we said to cover all the points, phi would cover 2 pi. Now, once you decide that, then theta, it only needs to go from positive g to negative g. If it goes over again, it's going to retrace the points that it has already done. So theta actually goes from 0 to pi, not 0 to 2 pi. So let me write that down. So theta will go from 0 to pi. All right, and I still have d phi integral. I said, doing the phi integral would get rid of x and y component, but we have to keep it for the g component. So phi, as we discussed before, will go from 0 to 2 pi. This will be the d phi integral. All right, let's write down the whole integrand. It's going to be k rho times s squared sine theta. I have all those terms there, so let me write that down. R minus s cosine theta. I guess that's it. I don't need to write g hat since I'm talking about g component. Divided by s squared sine squared theta plus r minus s cosine theta squared, whole thing raised to the power of 3/2. All right. Anybody here know how to do this integral? I don't. And actually, before starting on this video, I tried doing this on Wolfram Alpha. Wolfram Alpha runs out of time. So I'm actually going to have to do this on Mathematica. And I will explain as I enter this exact expression into Mathematica. All right. So I'm trying to evaluate the integrand. So I know what the result of the d phi integral will be, and I have some hope that ds integral will actually be simple. The integral that I'm worried about is theta. So let me do that. So I will write down everything except k and the density. So what I want to do is I want to integrate s squared times sine theta times r minus s cosine theta, the whole thing divided by s squared sine theta squared plus r minus s cosine theta raised to power of 2. The whole thing raised to power of 3/2. And we want to evaluate this for theta. That's the one I'm trying to do, one I'm worried about. So theta going from 0 to pi. Alright, I'm going to hit evaluate. And it's going to take a long time. So I will just edit this video. Oh, so after about, let's see, after about 3 minutes of calculation, that's the answer that I'm getting. What is that? So as you look at the conditions that the Mathematica is giving you, I hope you realize that Mathematica was treating these variables S and R as way more general than we were thinking. I mean, we know what S and R are. They are radius, they are positive numbers. In fact, we can even say R is greater than S. So we know all that. Mathematica doesn't know that. So what I'm going to do is I'm going to redo the calculation. Same integrate, but this time I'm going to tell Mathematica to assume. Assuming that, well, for one, S is greater than 0, and R is going to be always greater than S, because it's outside the sphere. Okay, assuming that, do the calculation again. Hopefully this time it won't take quite as long. Alright, so we get our answer after only about 30 seconds. So alright, that's our answer. So this is the result of the theta integral. So let me use this to simplify the expression we had before, and maybe I can do the rest of the integrals myself. Alright, the result of doing the theta integral was 2s squared over r squared for all this complicated expression here. So let me write that down first. So k rho times 2s squared over r squared. Alright, let me write down the rest of the remaining integrals. So I still have the ds integral going from 0 to r. I still have the phi integral going from 0 to 2 pi. And you know what? The rest of this integral seems doable. So for phi, all this expression does not depend on phi. So it just works out to be multiplying by 2 pi. The integral with respect to s, well, s squared, I know how to integrate that. So let me write out. So multiplication by 2 pi for the phi integral times. Let me write out all the constants that I would factor out. So that would be 2k rho over r squared. And now the antiderivative of the s squared. Well, that's going to be 1/3 s raised to 3rd power evaluated from 0 to r. Alright, let's plug all this in and see what we get. So we get, let me factor out k and r squared out to the front. K divided by r squared. And what's remaining is, alright, 2 pi times 2, so 4 pi divided by 3 times, let's see, what do I have remaining? Oh, r plugs into s, so r cubed times rho, density. Does anything look familiar? Yeah. So this is just the total volume of sphere, which means volume times the charge density. All this is the charge of the sphere. So you get this result. Electric field due to the uniformly charged sphere at some point distance r from the origin is equal to K times charge of the sphere divided by r squared. Well, that's what we would have gotten if we were dealing with the point charge at the origin. And some of you might recall this from physics 4a, that with the gravitational forces, if you are dealing with the spherical bodies, then you could treat it as if all the masses were at their centers. Well, this is why. We didn't do this calculation in physics 4a, but well, we just did it in physics 4b using the electrostatic force, which has mathematically identical form to the gravitational force. Alright, so this is it. That's it. That's the simple result. Let me scroll up and just write this down. So the electric field due to the sphere here. Well, when you finish all the calculation, then result you get is electric field is equal to K over R squared. And if you want to write your answer in terms of what's given here, then the volume 4 pi over 3 times R cubed times the charge density. That's it. That's the electric field due to a uniformly charged sphere. And you saw how mathematically complicated this was. You're going to see with the Gauss's law how simple this becomes. In fact, this is the simplest application example for Gauss's law. Really, this is the reason why we will spend a little bit of time covering Gauss's law, and this is why Gauss's law will be so important for the rest of electrostatics. It shows you how, with the exploitation of symmetry, you can do a problem in such a more simple way than you could do with anything else, really. I think it doesn't provide a lot of intuitive handle on electric field. To the extent it does, it tells you to rely on your intuition for electric force. So if you want to figure out the direction of electric field, imagine a positive test charge being someplace, and whatever force that positive test charge would feel, that's the same direction that electric field should point in. I have both some kind of instruction and the simulation there. All right, so I mean, yeah, it says uncheck electric field. So I want you to be able to sympathize with a real physical lab setup, where when you have some charges, you don't see electric fields. Electric fields are not something that become visible in the space that you have in front of you. Nonetheless, it is property of space itself. And the way we test those properties of space is by placing sensors in space. And these sensors are what we call these sensors are sometimes what we call test charge. It can be thought of as a very small amount of electric charge, positive electric charge, that would be pushed in the direction of the electric field. So this is really the reason I tell you to turn off the electric field, so that when you run this simulation with the electric fields on, you are really getting more information than you would in a real lab. Because in a real life lab, you don't literally see the electric field, but you know it's there, you understand that it's a property of space, and the way you know it is because you know if you place a test charge somewhere, the test charge would act according to the electric force, which comes from the electric field. So yeah, move the sensors around. Oh, 1 nanocoulomb charge. Let me move. So with the electric field turned off, if I have sensors around 1 nanocoulomb charge, you see that all these fields, they always and consistently point away from that positive charge. And if I go closer, it gets stronger. So, well, that's the kind of how you would be able to measure the electric field. And this is the visual representation of what that looks like. And when you replace this with a negative charge, you can, well, when they're right on top of each other, they cancel each other to zero. When you just replace it with a negative charge, then you see that all these electric fields, they go towards the negative charge. And that represents the attractive force that positive test charges would feel around this negative charge. So this is the representation of the setup I have in the simulation on the other screen. And what I want to do here now is predict the direction of electric field based on what I know about electric force. Electric force is proportional to electric field. So if you have these test charges and you are trying to figure out what is the electric field at the location of these test charges, the first question you should ask is, imagine the test charge is positive, what would be the force? So let me do that one test charge at a time. For this test charge here, I can figure out the forces due to each of these source charges. So this positive source charge would produce a repulsive force that points that way. And this negative charge would exert an attractive force that's along the line connecting the two towards itself. Now, you should be a little bit careful about the magnitude. The magnitude here should be smaller than the magnitude from the closer positive charge, because I hope you are remembering in the back of your mind Coulomb's law, which describes the interaction between 2-point charges as being inversely proportional to the square of the distance. So those are the individual contributions to the electric force, which means by this factor of the test charge, these arrows, they can easily represent the electric forces or electric fields. Until you specify a scale with a particular unit, it's the same thing. So for the net electric field, which is always what we are talking about when we are talking about electric field at a location. So we are talking about the sum of all the electric fields. It should point, let me do the head to tail method. So using the head to tail method, about here is where the electric field should point to. That's a kind of, mostly away from the positive charge, but the pull from the negative charge has a slight effect, so that the electric field is pointing straight away from the positive charge. You can repeat this exercise for all the other test charges. So let me quickly do that. So here's the force due to the positive test charge, force due to the negative source that's attractive. Now, one thing that's interesting about this particular test charge is that it appears to be at the same distance from both of them, which means these two have the same magnitude. So when they add together, their vertical components will cancel out, and you will only be left with the horizontal component that's double the horizontal component of one of them. So this is the net electric field. For the charge here, I can kind of see by eyeballing that electric field is going to point in the generally the same direction, but stronger for really two reasons. One, this location is closer to the charges, and up here, some of those electric fields have to cancel each other out. But here, nothing will be canceling anything. Positive charge is pushing it away to the right, negative charge is pulling it directly to the right. So for the fields down here, I feel like I can do a bit of make a symmetry. Wait, well, for this, I can make a symmetry argument. I can imagine doing this. I can imagine taking a line between these two and take a mirror image. So everything up here gets mirrored down here. So when that happens, the mirroring thing should be mirroring the electric fields as well. So I should have electric field from positive charge pointing that way, electric field from the negative charge pointing that way, and the sum, the net electric field, should be pointing this way. And I hope if you go through it in detail, you'll find that to be the case as well. I need a little more careful work with this last test charge. Let me just work through this one normally. So I'm gonna do the same thing that I did up there with this test charge. So the negative source charge here should be exerting an attractive force along the line connecting the two. So here's the attractive force. And the positive source charge should be exerting a force that's pointing away. That's a smaller magnitude than this inward one. So you look through it and imagine adding these two together, then it points this way. That's the net electric field. So that's the prediction for the electric field at each of these locations. Okay, so I have positive and negative charges. Let me place all the sensors right in the middle between them. All right, that's the right direction. And this looks kind of like a square, so I'm going to assume this is a square and place the second test charge directly above here, 3 blocks above. That's the one preserving the scale. So yeah, the pointing to the right. I guess a smaller magnitude than I would have guessed, but you know, I was drawing it qualitatively. And the magnitude there is the same as the magnitude here. And when I place the sensor here, it points roughly in the same direction that I drew. I mean, I might not have gotten the angle perfectly right, but it's point mostly up a little bit to the right. That's the general feature we are going for. And finally, when I put the sensor here, it's in the same direction, pointing a little bit to pointing upward and a little bit to the right. And yeah, that's the electric field. And yeah, and so whenever in a lab manual you see this, that's the place where I want you to discuss with the group what they have seen, make sure they didn't make any fundamental mistakes, and everyone's ready to proceed. And what I want you to make sure here was that people understood how you calculate the net electric field, and perhaps especially because you know all these weird directions, they are all right. I don't know if I have any intuitive feel for that, but something that you can always get intuitive feel for are simple pictures like these. All right, so that's getting feel for the electric fields and superposition principle involving electric fields. So now, and when we enable electric field illustration, that illustration should verify what we are seeing here. So when I turn on the electric field, this is what you see. Now, the simulation doesn't show electric field at every single point. I mean, as it is already, it's quite a bit distracting. It's this I think it's called the vector field. If you're taking Math 3C right now, you'll see it maybe in the last quarter of your class, I think, based on what I see in the textbook that's supposedly for Math 3C level math. So this is called the vector field. I don't think you really necessarily need to know that. And actually, these test charges can basically act as each one of these points on the vector field. Now, for the ones that I've placed, you can see that they, make sense. Around here is where electric fields are pointing directly to the right. Now, it curves a little bit, both to the left of the midpoint and the right of the midpoint. But right at the midpoint, what you see is consistent with electric fields simply pointing to the right. And the electric fields here and here seem to match their neighbors, as in it's mostly pointing up and with a slight change in direction. So yeah, that's the electric field. And this is copy from your textbook. It's telling you how to draw electric field lines. And yeah, I'll point out the important things. This is one of the things I don't
necessarily like is where both the textbook and other things come up with an arbitrary number of steps. Here it's written as 5 steps or whatever. It doesn't necessarily have to be 5. It can be some different number. But anyways, so first a couple times, let me try following this here. So the question actually tells me to draw a simple set of electric field lines. It says positive charge and, well, just a positive charge. Huh? I can also do it for a negative charge. So with a positive charge, there are different ways to draw electric field. Let me review what mention of any of these the exercise makes. Let me go through the steps that I would go through if I'm going through it from scratch. So what electric field lines are they're representing something like a lines of force. That it's a continuous line that represents the direction in which force or proportionally field would point in. So one way in which to draw those electric field lines is by, especially if you have access to a vector field like this, is to follow the vector field. You can start from one of the places here maybe, that point. So the vector field value here tells me I need to be moving that way. And you continue to move that way until the next time you get a guidance. It says, oh yeah, continue moving that way. It says, continue moving that way, continue moving that way, continue moving that way. That's one. And I can do that for all other 4 nearest vector field arrow that's drawn there. So when I complete all those 4 lines, that does constitute electric field lines. And I can show with the strategy that they illustrate in the textbook that the lines I have drawn satisfy all the properties that they've stated there. So let me go through each property one by one. One is that electric field lines originate on positive charge. And they do. They come from this positive charge here. That's why I extended this backward so that they look like they're touching the positive charge. It says number of field lines is proportional to the magnitude of the charge. I drew 4 lines. I guess with this, it's kind of hard to tell. And because, I mean, I could have 2 charges here, but in terms of electric field lines, it doesn't look like anything has changed here. I think it's going to be easier for me to demonstrate that with the question 6. So let me wait until then to do that. It says at every point in space, the field vector at that point is tangent to the field line at that point. That's kind of how we drew it. At each time we reach the point, we follow the direction of the electric field line. And now 4 and 5 are interesting. I think I find the 4 the most interesting, which says that the density of field lines represent how strong the electric field is. And as you look at it, I hope you realize that, yeah, that's true. Because as you look at it, you look at the electric field density in this neighborhood, just how close they are. It's the neighborhood close to the charge where the electric field would be strong. And then you compare the electric field density out here, just how far away from each other, the linear distance-wise they are. So electric field is less dense around here. And that actually corresponds to the inverse square law, that electric force, hence the electric field, decreases as 1 over distance squared. So it's an interesting fact that is going to relate to Gauss's law, or the introduction motivation of Gauss's law. The number 5 is the one that's a little bit, I mean, that's technically true. I think the downside of sticking to that too much is, let me demonstrate what I want to show. It's kind of hard to show with one charge because it's such a clear diagram that there's no opportunity for electric fields to cross. Let me instead illustrate with this. So I'm going to try to do it here. Here's a positive charge here. And let me place another positive charge here. Oh, around here seems fine. Now, when you look at this and you try to imagine electric field lines here, it's quite easy to, especially if you start out in the, I don't know, wrong space or whatever, it's quite easy to make a mistake where, okay, electric field comes out here, electric field comes out here, hey, they cross over here. It's quite easy to do that. And what I want to say is, yeah, that's a mistake. Don't do that. What this statement really means is this. The electric field lines, they represent a single vector, which is represented by the net electric field, the sum of all the electric fields. So at every single one of these points, there ought to be one vector representing the one net electric field. So when you have a field lines that are crossing, like if you had the field lines that go like this, what that would mean is at this point, you don't have a well-defined electric field. So since that's a mathematical headache, that's why the field lines can never cross. So in a challenging setup like this, you should still draw your electric field lines so that they don't cross. They go maybe like this. That's one of the ways to draw electric fields near interesting points like that. So that's kind of how you draw electric field lines. And so these rules and the conventions for drawing electric field lines, they are useful because it illustrates, it's a visual tool. It's a graphical tool for gaining an intuition for something that is a very abstract quantity. And I can illustrate with question 6 and 7 how these simple rules illustrate the key features. So let me have positive and negative charge here, and I've done this before with you've seen this vector fields before. Let me try this without the aid of the vector fields, and just to try to follow the rules that I see here. Follow these rules here. And when I do, this is what you see. So I'm going to try to stick to rules number 1 and 2, which is they originate on positive charges and terminate on negative charges. So I should have field lines coming from the positive charge here, and I should have field lines ending at the negative charge here. And reading ahead, that the number of field lines are proportional to the magnitude of the charge. For both of these, let me draw 4 lines. It's a little bit sparse, but let me work with the 4 lines. How do I want to draw these? Let me draw it this way. I'm gonna kind of draw them like a cross shape. So by which I mean I'll have 4 lines that go directly horizontal and directly vertical. And I'm starting with very close to the charge, because very close to the charge, I can make the argument that whatever effect the other charge has, it's very small near the other charge. So at this point, the positive charge rules and the negative charge, it's so far away that you can ignore it. So let me draw it this way. So drawing up to this far, I've obeyed the rules 1 and 2. And now I can't, oh wait, I haven't fully obeyed it, because if I simply end the line here, then it ended where there's no negative charge. So I have to continue this line and continue this line and connect it here. And I guess with these 2 field lines, if you were to draw something that looks like this, guess I can't quite stop you based on these rules, which is where you have to be reasonable and remember that these field lines represent electric fields. So if you're somewhere out here, you've seen before with the earlier exercise how the field, the electric field here kind of pointed a little bit to the right because of the negative charge. So I need to start to put that in, and I know around or at points along this line, let me mark that in yellow. It points along this midpoint between the two charges. I know the electric fields have to point horizontally. So with those directions of fields in mind, let me draw the picture so that this field line actually connects to that field line. It might look something like this. I mean, it's a bit crude. This part especially is especially crude, but something like this is something it respects all these rules. And for the electric field line here, I can say that there's nothing that would cause it to bend up or down. So it's going to go out to the left, out to infinity. And same for this field line here. It comes in from out at infinity. And when I turn in on the electric field, yeah, this kind of matches, kinda. These horizontal lines match how they should look, and these curved lines kind of match how the electric fields look based on the vector field representation. Now, here's the interesting thing that where some of these rules help, that the number of field lines are proportional, and that the field lines can never cross. So let me do what's represented in question 7. I think that was where I think I did 2q instead of, double the charge on the left. So let me do that. So when I have double the amount of charge, I haven't turned on the electric field yet, so I don't know what that looks like. What I do have a sense of is the positive charge now needs double the number of electric field lines coming out. It needs electric field coming out here, 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 here. Now you see the bit of a conundrum I have, which is that these field lines, they have nowhere to go. It can't end here because then it's no longer proportional to the negative charge. So it can't end there. And it also can't go out to infinity because it's trapped. It can't cross the other field lines. So what that means is there's a more extensive modification necessary. With those addition of 4 lines, I actually have to change how I drew these field lines as well. So that what I now can do instead is these lines will connect to the negative charge here. This line will connect to the negative charge here. And though I think in the process of that happening, what you will begin to see is that around this point, it's no longer electric field pointing horizontally. It's now in some diagonal direction. And these field lines will, I guess it depends. I think I'm okay drawing these 2 field lines going out to infinity. And this is a matter of geometric representation. I think I can have one of these 2 lines end on the negative charge, but not both of them. Maybe the way I have it now is fine. There can be a electric field line from negative there. There will still be a kind of line of electric fields that's along the horizontal there. So I think what I can do is I can have this also going out to infinity. So trying to follow those rules about drawing electric field lines, you now get some sort of asymmetric picture, which will be confirmed when you plot the electric field vectors. You see that they are kind of more radially going outward, and around this midpoint, the field lines are no longer horizontal except here. And and the field lines kind of come in steeper around the negative charge here, and there's other field lines that you can imagine just going out to infinity, or yeah. So that's the intuitive picture of electric field lines.
Get practice then. So I want to use the remaining time we have to just play with the other simulation. So this is an example of a simulation that I thought I could use it to illustrate electric field lines. And one thing you will see is it's got limited choices. So with the PHYS simulation, I could set up a potentially arbitrary arrangement of charges. With this simulation, there are some presets, which of which there are a lot. Presets, it's got a lot of presets, like 3 dozen or so. But it's a preset. I can't grab the charge and move it around. I'm changing the view right now. See that 3-dimensional axis that's moving around. But I think it'll still be good to illustrate the 3-dimensional nature of electric field lines and look at some of the interesting things. So now the display of particles, that isn't what I'm interested in. So let me, as mesmerizing as that is, let me move away from that. So electric field vector is what you saw with the PHYS simulation. I see. It's doing that view because it does show G-slice. Let's say no slicing. So this shows the whole 3-dimensional vector field view. So let's stick with the 3 dimensions, because if we wanted the 2 dimensions, we can look at the PHYS simulation. So this is kind of the same version as what the PHYS simulation is doing. And what I really want you to show with this is not the field vectors, which again the PHYS simulation does, but field lines, which PHYS simulation doesn't. And you can kind of get a sense of how these lines are arranged as you kind of take it and rotate it around. I hope you get a sense that these lines are isotropically oriented, in the sense that as I grab this view and rotate it around, like there are some views where lines line up in such a way that you see gaps through it or whatnot, but that's just a quirk of how it's drawn. It picked this plane and then a plane a little bit rotated, but like if you take a more statistical view, no matter how it's oriented, the density of lines remain about the same. It's radially symmetric. It's rotationally symmetric. And if that's not quite evident as you look at it, then that's where slicing can be useful, because the slicing shows projection of these lines onto one plane. And when you kind of rotate it around and look at the plane head on, then you can see, well, it should have been possible to see more easily that these are uniformly spaced, but I think there's a bug in the programming. Like these look denser than these, and that's definitely wrong. So let me move away from point charge. It's a little too boring. I'm sure or actually before I do that, let me see X slicing. Yeah, these angles being different, that's some bug in the programming, I'm sure. So let me look at dipole, where it's more interesting. With dipole fields, it's more interesting a few ways. So I think the least confusing way to look at dipole charge distribution and electric fields of a dipole charge distribution would be to do it with no slicing, so that you can see the whole 3-dimensional view of the dipole field. You can see, can I show I can't tell which is positive and which is negative. It doesn't quite show the direct. So when we draw electric field lines by hand, we usually indicate the direction of the field line. So let me pretend that this is positive charge and this is negative charge. Then as we draw the field lines, we would add a little bit of arrows so that we can tell the direction of the field. So if I'm drawing these field lines by hand, I would have, so assuming this is positive, this is negative, I would draw arrows that go in this general direction. And all the lines out of here will be pointing away from the positive charge. all the lines into the negative charge will be pointing into the negative charge. This simulation, for whatever reason, the author decided not to do that. Probably because I think those arrows could really clutter up the diagram. So yeah, this so with the three-dimensional things, you kind of have to have the ability to grab and rotate in to get the full three-dimensional sense. And when we talk about dipole fields, this is what you should imagine. And I think the way we usually draw it, we draw it with, I think, this G slice in mind. So this is a more common view of dipole field that you might see. Can I? Oh wow, I can move the slice around. Oh, I didn't know that. Yeah, so I can move this slice around to take like a different, like what is it, MRI or a CT scan kind of view. Take a different cross section. Cool. Didn't know I could do that. And you can also, when you take a X slice, it can look a little bit weird. Like, I guess because they don't have the arrows, it doesn't. Oh, sure. Yeah, I think X slice just looks weird. Three-dimensional view. So I think I mentioned this in the virtual class session last week, that as we start electricity and magnetism, we really have to keep reminding ourselves that space is three-dimensional. Even when we don't explicitly invoke things that need three dimensions, all the things we see, it kind of only makes sense in three dimensions. Gauss's law only makes sense in three dimensions. So even when we have arrangements that are essentially two dimensions, like infinite plane of charge, the Gaussian surface we pick will be like a pillbox surface that is actually three-dimensional. So okay, that's dipole. Let's see if I can. Quadrupole, I have no intuition for how. Alright, that's just way too complicated. Yeah, I'm just gonna move away. Charged line, that can be interesting. So with the charged lines, if you look at it from one perspective, where the line is, either directly, where you can imagine the line coming towards you, or towards you, or going away from you, then the electric field lines actually, they kind of look like the field lines of a point charge instead of the charged line. Oh wait, it resets the view each time. That's annoying. Now, it's when you consider the three-dimensional view that electric fields due to charged line looks different from electric field due to a point charge. And actually, when we derive the formula for this, the strength of the electric field, it changes differently. With the point charge, it goes as 1 over r squared. With the infinite line of charge, the field strength decreases 1 over r instead of 1 over r squared. So it's possible to take a kind of deceptive view that doesn't have you fully appreciate. Like this makes it look like it's a point charge, and this view, well, maybe this view is a little bit harder. Can I get rid of perspective? I don't think I can. Well, there's a view where, so if you imagine not having this perspective, then charged line can look quite similar to charged plate, infinite plane. Infinite plane, where like electric field lines look like they are going straight away. So if you draw this perspective view of electric field due to charged plane, they can made to appear similar to this particular view of the infinite charged line. But the difference will be here, as you go farther away, electric field decreases as 1 over r. If it's an infinite plane, then these fields are actually constant. You can see it in this illustration. It's all same color, green, meaning whether you are close to the plane or far from plane, it's the same magnitude. It's one of the things you can derive using Gauss's law. And I think I did one by integration as well. But Gauss's law is a lot easier. Let's see, what other example I want to look at. Conducting plate? I don't know. It's interesting thing to look at. I don't know if there's anything I can say. Finite line pair can be interesting. So I think this is one where they are equal charge, like one positive, the other is also positive, and the finite line dipole would be where one is positive, the other is negative. And like from one view, it looks kind of like a dipole field, and from other view, I don't know. Oh wait, it's a finite line. Oh, that are they? Yeah, okay. So there's a finite line. Yeah, so when it's a finite line, it's different. So the length of the line charge is about that long, and yeah, charge line. Oh, I see dipole lines. This is what I was imagining. Yeah, okay, yeah. So this is the one where you have two infinite lines, one positive, one negative. And then, like from a certain view, it kind of looks like the dipole field, but from a different perspective, it looks really different because there's this translational symmetry that dipole doesn't have. Translational symmetry along the line. Um, yeah. Is there anything? Oh, conducting sphere and point. So this is a kind of an upper division material. How to handle electric field due to a conducting sphere and a point charge. We won't handle it. In upper division, they can handle this using something called method of images. I think that's probably all the things. So yeah, let me just end that here. I do think this is a good simulation to kind of help you visualize electric field lines, especially in three-dimensional setting. It's this kind of rotating shapes. It's the kind of thing that it's good to have a visual representations of, so that you can, where maybe your imagination fails, you can use computerized tool to help with your imagination along. Okay, so what this entire exercise was really leading up to was the graphical representation of electric flux, because that's the piece that you need in order to make an intuitive sense of Gauss's law. Gauss's law is stated in terms of electric flux. So if you don't have a good grasp on what electric flux is, one, it's hard to understand Gauss's law. And two, I think at the end of this activity, we can actually see the intuitive conceptual reason that Gauss's law exists. I mean, I wouldn't call this a derivation of Gauss's law, because that is impossible. Gauss's law is the fundamental law. You don't you derive other things from Gauss's law. You don't derive Gauss's law. So you guess at it. Sorry, said internet connection stable. I hope I'm still coming through, or if my yeah. Anyway, so let me read it through here. See how many of these I want to do. Let's see here. I think I should at least start by drawing some area in a electric field representation. Okay, so what this is a side view of infinite plane. And I want to consider an area for calculating flux out of. The simplest, easiest area of a sort is area that's perpendicular to the field. So I can imagine a rectangular area of area A that lies here. And I'm drawing the side view again. So, it's like you are looking edge on of an area. If you tilt it a little bit, then it'll it'll start to have some representation in 2D dimension. So we're not going to do that, but imagine some area there, and sketch this picture and calculate the electric flux. Well, that's pretty simple. For infinite charged plane like this, I know that my electric field here is uniform. It's one constant value. So, so as I'm imagining calculating this quantity, E dot dA over this area, I don't have to worry about E changing, because it's not. And by the way, if E changed, you don't want to set up the arrangement so that it doesn't change over the integral. Anyways, it's already not changing, so I leave it. So the thing I have to handle is the dot product here. And if you watch the lecture videos, I think you will see me note that the direction of an area vector is defined by looking at what is the normal vector for the plane. So, and there's something about the sense of direction for the normal vector. Here, I just chose that direction in a way that I know will make the dot product come out positive. So, okay, here I just argue that electric field should be constant, not changing. So when I imagine integrating this over the area, I'm simply going to get that the flux here is equal to electric field, the constant value, dot product with the area. And here they happen to be in the same direction, 0-degree difference between them. So the flux, which is a scalar quantity, is just electric field times area. That's it. That's the flux. I think the next question was a bit more substantial. Let me take a look. And it says, yeah, and you know, I said let's start with an easy case. It was easy. Let's modify the case by rotating the square. And define the coordinate axis. Do I want? I don't think I have to define coordinate axis, so I won't. So we can look at this picture here and see how that flux would change. Well, let's do some of that mathematical work here. So that's what you can imagine doing. And you can see here that this is the direction of the electric field. Now E dot dA becomes more interesting. So the more general expression for that dot product there is this. It's equal to the magnitude of the electric field times the magnitude of the area, or just the area, magnitude of the area vector. And we have to handle the dot product. So the dot product will give us the factor of cosine of the angle between these two vectors, or for purpose of simplicity, I can just say cosine of theta. That's going to be the angle between the two. So yeah, I guess if I plug in what cosine theta is, then I would get this. Electric field times area times cosine of 45 degrees. That sounds like 1 over root 2. So that's the electric flux. That's it. So what you see with the dot product definition of electric flux is that this dot product contains some information about the relative directions of the quantities. That when you have electric field pointed in certain way, when the area was perpendicular to the electric field, when the surface is perpendicular to the electric field, then it captures the most flux, and it's captured this way because of the way we define the area as a vector. When the surface is perpendicular, that means the theta is actually 0 because the normal vector is parallel to the other vector that's perpendicular. So cosine of theta is 1. You get the most maximum possible value out of the dot product. Anything else, when you rotate the area relative to that orientation, then you get flux that's decreasing from there. And that's represented here, that's captured here. When theta is anything other than 0 degrees, you get less value, and I got this 1 over root 2, not 1. And I think this is actually the next question in the lab, which is, let's see, would it be possible to arrange it so that the electric flux through the square is 0? Yeah, I think you can imagine that. Two different ways to get at it. You can orient it in a way so that one way I think that's easier to get at is the mathematical way, which is you look at this expression and you realize, if theta is equal to 90 degrees, then cosine of 90 degrees is going to be 0, so you'll have 0 flux, and that corresponds to, let me do this rotating thing again. let's see here. Let me rotate it additional 45 degrees. Yeah. So with the area oriented that way, you'll get zero flux based on the math here. And this is the thing I want you to get at. This is the reason I want you to talk about the electric field lines in this context and have you be in the mindset of looking at. You can see that all these field lines that were going through the area before are now going to be missing the area. Electric fields are parallel to the plane, so they don't go through the plane. So the flow of electric field through the area is zero. That's really why we call this quantity flux, because the physical intuition that makes most sense for this quantity in the way it's mathematically defined is some kind of a flow analogy. With all the caution that with electric field, nothing is actually flowing. It's a mathematical property of space. Nothing is actually moving. But the imagery that's most useful is a one over flow. So with the area oriented this way, no fields are flowing through the area, so the flux is zero. And that statement is backed up with the mathematical definition of electric flux. Now, with the practice out of the way, let's consider more realistic and relevant situations. And I think this is the situation that that I was hoping you will see that leads naturally to Gauss's law. Now, this one, let me go through that. I think we got this far, spent a fair amount of time getting this far. I think let me just follow this instruction word for word. It says consider a point, positive point charge. What is the net flux out of a sphere of radius r with a charge q at the center? All right, let me draw that. So I have charge q, and I'm going to draw my sphere so that the q is at the center of that sphere. Let me draw my sphere of radius r with the charge at the center. So I'm going to draw the kind of the side view of the sphere, and because it's a three-dimensional object, I have to kind of add other indicators to have you imagine that it's a sphere surrounding the charge. And it says that choose the normal vector so that every point on the sphere, the normal vector points outward. That's the convention that I was referring to. With the closed surfaces, the convention for the, so with the normal vector, you only have two choices. Is it one way or the other way? Those are your two choices. And when you have an open surface, you have a free choice. You can go with either. When you have a closed surface, then the convention is that the outward pointing normal vectors are the positive normal vectors. That's the convention. So n points outward, and that direction will actually turn out to be fairly useful because as you look at it, so you already know what the electric field of a point charge looks like from Gauss's law, Coulomb's law, and those radially outgoing directions, they happen to match those radially outward pointing normal vectors. So that'll actually make my dot product super easy. So let me write down the full expression for electric flux and point out the simplifications. The electric flux here is integral of the E dot dA over the surface of the sphere. Which means, let me handle two parts separately, the magnitudes and the directions. So, so the magnitudes will be the magnitude of the electric field as a function of distance, and the area element, dA, that's something that I'm going to have to work out. So that's one. And because I have the dot product here, I need to mind the directions. And the directions will be the r hat vector, the radially outgoing r hat vector, dot product with the n hat vector. And what I was pointing out was that at every point on the sphere, these two vectors are actually in the same direction. So this product that I was separating out, that's just one. Because it's so simple, I want you to make sure to highlight it and make sure you don't miss it. Because if it was some value other than 1, then there's no chance you would have missed it. But because it's so simple, it is easy to miss it. And for the circumstances where you can't miss it, I want to highlight it. So directions are simple. Now, all I have to deal with is this magnitudes. And there's actually additional simplification here, which is the fact that we are doing the area integral over the points on the sphere. And what's useful here is that every point on the sphere is at distance r. And you know from Gauss's law that the electric field of a point charge is Coulomb constant times the point charge q divided by r squared, which means on the sphere, this distance r is not changing. So over the surface that you're integrating, this electric field here, it's actually constant. So there's no, I can pull it out of the integral. That's the simple thing to do. So let me do that. I can pull that out of the integral, and then I have this integral of the area element over a sphere. And I guess I could actually write down the area elements and actually do the integral. You know, I can do that and get the correct answer, or I can do the easy thing and recognize that what this is giving me is a surface area of sphere. So I happen to have that memorized, like every good physicist, 4 pi r squared. So I'm just gonna plug that in. So here the flux, the total flux ends up being the value of the electric field. That's that there. Let me write that down. K E, the Coulomb constant times the charge divided by, and I'm going to be careful to put in the actual value of R, which is capital R squared. That's the electric field times the area, 4 pi R squared. Oh, R's cancel. So it ends up giving me 4 pi times KEQ. And later on, I hope you recognize that this is actually what would have been given by Gauss's law. We just did it the long way and did a calculation using Coulomb's law. Coulomb's law and Gauss's law are equivalent to each other, so they both should give the same result. So, all right, that's the easy calculation. Show your work with the explicit calculation. Make sure to cancel out anything that cancels out. Show the cancellation with all that. Let's see what's next. Consider the following change to the setup. If the sphere has been placed so that the charge is not at the center, but r over 2 away from the center, could you do a calculation similar to Q12? I mean, I can. It won't be similar. I think that's what the bonus point is getting at. So, you know, I can, in the sense that, all right, I can set this up, I can write this out, I can do the dA. Now, this won't simplify this way because if the charge is over here, then now the radial direction away, it's not going to necessarily be the same direction as the n hat. Like over here, the r hat goes that way, n hat goes that way. So it won't simplify nicely this way, all right? And I won't be able to pull out the electric field because the electric field magnitude here will be stronger and versus electric field magnitude here, which will be weaker. And now, if you know Gauss's law, you know that the result here, that this is equal to that, it actually does not, that result itself does not depend on symmetry. Gauss's law gives you that as a matter of statement. So that's one way in which you could do this flux calculation. You appeal to Gauss's law, which gives you the flux directly. That's one way. And in a face-to-face lab session, what I would hope that this activity would lead to is that you can actually intuitively guess what the Gauss's law gives you. It's this. In the previous exercise, you saw how flux, the flow of the electric fields through a surface, it kind of depended on how the electric fields appear to go through a surface. So there's a way to estimate or calculate flux by counting how many electric field lines go through a surface. Now, it's a qualitative thing, it's a proportionality thing. So, here I see 8 lines going through, and you can say my flux is 8 lines. You have to tell me exactly what the quantity is. But what I can tell you is that these 8 lines going through, that corresponds to this amount of flux here. And this is what I want you to consider. When let me do it this way. When I move this charge so that it is over here, imagine moving all the electric field lines and again counting how many electric field lines go through the surface of the sphere. Let me actually do that. Let me draw a charge here, draw a sphere around it, and let me draw the same number of electric field lines as I have done before. And when I draw those the same number of electric field lines as before, you will quickly see that, oh yeah, the same 8 lines have to go through the surface of the sphere at some point. Now, for some of them, they now go through earlier, by which I mean, not actually time. I'm trying to follow the flow analogy. They cross the surface at a closer distance, so the electric field strength would be greater there. So at some places, they happen, quote unquote, later, by which I mean farther distance, so the field magnitude is weaker there. But one thing that won't change as you move this charge around within the sphere is that all these 8 lines have to escape the sphere at some point. So in terms of counting number of electric field lines, it'll be the same. So from this graphical representation you see here, you can, with some intuition around how electric field lines are related to flux, you can see that as you move this charge, the total electric flux hasn't changed, and frankly cannot change for geometric regions. I'll put a bit of a qualifier there in a bit. But I think I'm hoping as you are considering this intuitive picture, that you get the intuitive feel that as long as this charge is inside the sphere, that this result that we calculated for a highly symmetric setup, it remains to be true for a situation that's not very symmetric at all. And this is the intuition that I'm hoping will lead to your intuition for Gauss's law, that the Gauss's law is true. Now, there is a, I guess I'm jumping to epilogue there. Should I do question 14? Let me do question 14. I think I can do question 14. I think I can do question 14 exactly as stated, and a slightly modified version. And I think I can use that to continue to build this intuition for the connection between electric field lines and flux, and how that relates to Gauss's law. So let me draw this picture. The picture here is, I have a charge, plus Q, and a sphere around it. That's the sphere through which I'm gonna calculate a flux. And I can imagine placing a negative charge at 2 different places. The first is where question 14 tells me to, way out here, minus Q. Now, as you imagine drawing the electric field lines, I want you to think about how many electric field lines still go through the surface. If I'm still drawing 8 for one charge, if all these 8 lines still have to go through the surface at some point. And I hope you think through it for a bit and then realize, yes, the answer is yes. It relates to one of the rules about drawing electric field lines. One of the rules was that these electric field lines, they begin and end on, they begin on positive charge and end on negative charge. So these 8 lines, they begin on the positive charge, and until they encounter this negative charge, they can't end. So I can choose to end the 3 of these lines on the negative charge, and actually 2 more. These 2 can end on the negative charge. But in order to land on this negative charge, they all have to go through the surface at some point, which means this negative charge being present there, it didn't change any of the flux through this surface, because negative charge being out here, it didn't change the fact that all these 8 electric field lines have to go through the surface to get to that. Now, when the negative charge, so this is the question that the question 14 didn't ask, but I'm gonna ask anyway. When that negative charge is inside the sphere, that changes this picture. So when I have, let me just redraw this entirely. So when I have positive charge here and the negative charge here, then following the same field line drawing rules, this is what you have. 8 lines starting from here, and all those 8 lines either going out to infinity, like this one, it'll just go out to infinity, or landing on the negative charge. It begins on the positive charge and ends on the negative charge. And as you consider these field lines, I hope you see that the net electric flux through the sphere will be 0. Now, it doesn't mean there aren't electric field lines going through the surface. It's just that when you finish counting them, all the ones that go out and all the ones that come in, ones that go out are counting as positive, ones that come in are counting as negative, and they have to add up to 0. And any line that goes out here has a part that comes back in, or any line that's exiting here from the positive charge, there's a corresponding part that enters and ends on the negative charge. So when you finish counting all those crossing points, they add up to 0. So, and you can see, I hope you are beginning to see intuitively how that matches with what Gauss's law says. Gauss's law only considers the net charge inside the volume that you are considering. Here, the net charge is 0, and that matches with the net 0 flux for this particular situation. And all of this is leading up to the intuition for Gauss's law. And what I want to say and end with is what Gauss's law really says, and which of the electric field line drawing rules are an expression of Gauss's law. So, yeah, the questions are leading you to Gauss's law on your own. Gauss's law, which says this, it's quite intuitively true. And it's saying, this is the thing it's saying, that electric charges are sources of electric field lines. The rule that we are trying to obey from above is this rule here, which is that electric field lines, they originate on positive charges. So positive charges are sources of electric field lines, or they terminate on negative charges, or the negative charges are sinks of electric field lines. This is the field line version of Gauss's law. As long as this is true when you're drawing field lines, Gauss's law is true. And as long as Gauss's law is true, we must have this as one of our rules for drawing electric field lines. So yeah, that's introduction to Gauss's law. It's a quite lengthy introduction. Again, the original design of this activity was that I wouldn't be lecturing for 2 hours. You would be actually doing this activity, and over the period of 3 hours of lab time that you would figure this out on your own. Sorry, I wish I knew a better way to do this online.